Okay, formal charge is sort of the last Lewis structure skill. Um, you see it sometimes in textbooks as electron bookkeeping. It is pretty quick and easy, actually, and the point of it is it's a way of looking at how charge is spread out around something that is covalently bonded. Because even though electrons are being shared, sometimes atoms are kind of holding more of the charge than the others. And if we have something like a polyatomic ion, this is a way of assessing like where is the overall positive or negative charge being carried within that particle. It also gives us a way of assessing Lewis structures. Sometimes we're able to draw more than one Lewis structure for something, and this is a tool that we can use to decide which Lewis structure is kind of preferable and more stable. Okay, now in the system of formal charge, we ignore electronegativity. So we don't think of like fluorine owning electrons more than oxygen or more than nitrogen, even though in reality it would. So there are like definitely some limitations and simplifications in this formal charge system. We also look at all of, when you have something bonding and it has its own lone pairs or non-bonding pairs, we're going to say that the atom owns those electrons completely. And then because we're ignoring electronegativity, when we have a bonding pair, we're going to treat it like each atom owns one of the shared pair. And then basically what I do, I mean, there is an equation you can use, but I find it more complicated than it's worth. I just look at the number of valence electrons and I compare it to the normal number that that atom would own. And that's how I come up with the charge. Okay, and the overall, the formal charges should add up to the total charge on the species. So if it's a molecule, it should add up to 0. And if it's a polyatomic ion, it should add up to the charge on the polyatomic ion. All right, let me show you a couple here just so we see. All right, we've got NH4, we've got ammonium. We should be able to draw ammonium pretty quickly like this. Okay, now in formal charge, there are no lone pairs in this example, so we're just going to take every bonding pair and we're going to split it up as though it were two separate electrons, and one electron belongs to each atom. So if I just do this, that's looking at the nitrogen, and then I kind of circle. It's almost like going back to the Bohr model days and kind of looking at these atoms with these circles around them. Okay, in this drawing, every hydrogen has one electron. Okay, it owns one electron. So there's two electrons in the bond, and in this system, we treat it like every atom owns half of the bond. So each hydrogen owns one electron, which is the normal number of valence electrons for hydrogen. So all these hydrogens have a formal charge of 0. So they don't really have a formal charge. The nitrogen, on the other hand, has 1, 2, 3, 4. So nitrogen has 4 valence electrons in this drawing. Nitrogen normally has 5, and so that means it's missing a valence electron, and that means that the positive charge is on the nitrogen in this drawing. So that means nitrogen has a formal charge of 1 plus, or actually I think I need to write it the other way, plus 1. So its formal charge is plus 1. Okay, so we know that this thing has a plus 1 charge, and the formal charge has allowed us to say, well, it seems like the positive charge is sort of on the nitrogen, and the hydrogens, at least how they're drawn here, aren't really carrying any of the charge. Now that may not be entirely true in reality, but this is just a simple system to try to assess how the charge is spread out. So we would say the nitrogen is plus 1 and all of the hydrogens are 0. Let's try the carbonate one. Okay, if I draw carbonate, I do this. In the end, you could be using the 7 steps to try to get you here, but you need to use 4 bonds, and we get this drawing for our Lewis structure. And we know that this can do resonance, and so actually the bonds are all like 1 1/3 bonds, which is why, again, formal charge is kind of limited. But given this drawing, if this was our Lewis structure and we weren't thinking about resonance, we would go through and we would count those electrons again. So I'm going to split these bonds. I'm going to show the ones that go to oxygen in red, and I'm going to show the ones for carbon in purple. just splitting every bond in half and then circling. So this carbon has 4 valence electrons. That's the normal number that it has, so its formal charge is 0. This one at the top has 6 valence electrons, which is the normal number of valence electrons for oxygen, so it has a formal charge of 0. But these two both feel like they have 7. And 7 is 1 more than oxygen's number of valence electrons. And so each one of these ones in blue has a formal charge of -1. And so what we're saying is that, at least the way we've drawn it, the negative charge is sort of carried by those 2 oxygens that I circled in blue. And the carbon and the other oxygen are not carrying any of the charge. Now, in general, the idea is for preferable structures, we want to minimize formal charges, like the magnitude of the charge. So the thing about delocalization and resonance is that actually it would help spread out this charge. And so the oxygens, the 2- is actually spread out across all 3 of the oxygens in reality, and they have formal charges that are less than 1, more like 2/3, -2/3. But you're not expected to do any fractional non-integer formal charges in the IB. So we just do it that way. Okay, so I'm going to skip ahead and get to the last thing, which is like, what can we use this for? So an example that we looked at a while ago when we first introduced resonance and delocalization was SO2. And so SO2 we drew like this. And we can draw resonance structures, but this is like one Lewis structure. And this Lewis structure follows the octet rule. But now that we've covered expanded octets, then there's also a way to draw this molecule where we expand the octet. And so the expanded octet approach is draw sulfur with its 6 valence electrons and then generally make the outside atoms have their normal number of bonds. And that's 2 for oxygen. So this is an alternative way to draw SO2. It uses the same number of electrons. It just takes this lone pair over here and it shares it with sulfur rather than having it be just on oxygen. So now we have an expanded octet Lewis structure. So either one of these is fine if you're not told to do anything differently. But now let's say we were given these and we're being asked to compare them and to decide which Lewis structure is preferable. So in this one, we do the same thing. I'm going to do it faster now, where I split each bond. Half the electrons go to each. So this oxygen on the left feels like it has 7, so it has a formal charge of -1. Whereas the one on the right feels like it has 6, so it has a formal charge of 0. And the sulfur in the middle is 1, 2, 3, 4, 5. 1 less than normal, so it's +1. So my formal charges add up to 0, which is good because this thing doesn't have a charge. And those are the values I get for this drawing. Now if I go over here to my expanded octet one, I do those circles again. This oxygen has 6, formal charge of 0. This oxygen also has 6, formal charge of 0. And the sulfur has 6, so formal charge of 0. So which structure is better? Well, the idea of formal charge would tell us that this structure is preferred. We want to minimize formal charges. Get them all the way to 0 if possible, or get them as close to 0 if we can't get them all to 0. You know, if you think about it, why would electrons hang out over here on this and concentrate themselves on this oxygen if there's an atom over here that's got a positive charge? If there's an option where that charge can spread itself out, these electrons are going to move towards this sulfur, and then they're going to, and by sharing with sulfur, it helps spread out the charge. So spreading out charge is always more stable. And so this structure minimizes formal charge. We have no actual formal charges. They're all 0. And so this is the preferred Lewis structure. When you get certain situations where you have multiple Lewis structures and all of them kind of have the same formal charges. So you get like, there's 3 atoms and you get 0, 0, -1, or you get -1, 0, 0. In that case, you should pick the structure that puts the -1 on the higher electronegativity element. Now, this is like a super rare occurrence that you would be asked to decide on something so nitpicky, but I have seen them do it once. So the preferred structure is the one where the minus charge is on the higher electronegativity element. So both of these structures, I haven't actually drawn them, I'm just giving you a hypothetical situation. Both of these examples, we've minimized the formal charge as much as possible. And I still can't decide. So in both of these examples, we have 0, 0, -1. So really like the size of the formal charges are the same. And so only when that's the case and you still can't decide, then it makes the most conceptual sense to put a negative charge on an element that really attracts electrons, that has a high electronegativity. So then this example, this scenario would be the preferred Lewis structure. Now, obviously, that's a little silly because formal charge by its nature ignores electronegativity, but sometimes formal charge doesn't help us enough. And so in that case, we're able to look at electronegativity to decide which structure is best. So formal charge is just a way at looking at how is charge spread out within a covalently bonded structure. It ignores electronegativity, and it can help us decide on which Lewis structures are more stable and more preferred by trying to minimize formal charges within a structure.